Hey, here we are, our first lesson, sets of numbers. I want to warn you that this first section is a little bit weird, but don't get too caught up in it. The important stuff is you'll see a lot of it and it'll make complete sense at some point here. So the idea of a set means a group, and it's a collection usually for us of numbers. Those numbers are called elements. But they could be variables. You'll see classes in college like abstract algebra where you have all kinds of sets and they're usually variables of some kind, letters. But for us, our elements are always numbers. A subset means that every element in a subset is contained within the set. The empty set, this symbol right here, it's a set with nothing in it. It's an empty set. Now, they have the numbers down here, and this representation is okay, but it makes more sense. I'll scroll down in a moment, but let's just observe a couple things. The natural numbers start at 1, 1, 2, 3. The whole numbers are the same as the natural numbers, but they have a 0 in them. So the natural numbers are a subset of the whole numbers. Every natural number is contained in the whole numbers. The whole numbers are contained within the integers. This is called a Venn diagram, by the way. The integers, though, have negatives, and none of these have any decimals or fractions. So all of these are contained in the rational numbers. A rational number is, and they use the symbol as Q. Notice the symbols here. Integers is Z, whole numbers W, N, natural. The rational numbers, Q, I think Q is in quotient. A quotient is division problem, is any number you can write as a fraction. Now all of these are rational numbers because I can take a natural number 2 and write it as a fraction. I can make it 2 over 1. I can make it 10 divided by 5. If you can write it as a fraction somehow, then it's a rational number. A rational number is always a fraction with integers. It could be negatives. Notice the integers have negatives. All of these things are real numbers, including the irrationals. Now, you heard me say a rational number is a fraction with integers, like 2/3 or negative 2/3. An irrational number can't be written as a fraction, as integers. There's no way to make a fraction that represents these things. So square roots that don't come out nicely are irrational, like the square root of 5. There's nothing times itself that makes the square root of 5. Pi is irrational. And these irrational numbers, if you continue to infinity, they're decimals that go on forever, and there's never a pattern. That's a characteristic of an irrational number. The decimals go forever, and they don't have a pattern. Whereas a rational number, like 2/3 is 0.6 repeating, or 1/3 is 0.3 repeating, they'll either terminate, meaning stop, or they'll repeat on forever, but in a pattern. Now they talk about some of this here, and I already talked about it, but this is what I really wanted to show you. Here are the examples. I can make a list of the natural numbers, 1, 2, 3. The 3 dots mean it continues forever. Always 3 dots. The whole number's the same except for we include 0, and again they continue forever. The integers are the whole numbers, but now we have negatives, no decimals, no fractions. They continue forever in the negative direction, forever in the positive direction. A rational number is a fraction. Any number I can write as a fraction. 1 1/4 is a fraction. It's 5/4. So any mixed number I can write as a fraction. A 0.5 is 5/10. It's really 1/2. That's a rational number. 0.3 repeating, I said a bit ago, is 2/3. That can be written as a fraction. So if I can write it as a fraction, it could be negative too, then it's a rational number. And remember, all these can be written as fractions because I could write 3 as 9 divided by 3 or 21 divided by 7. Irrational numbers can't be written as fractions. They're decimals that go forever and never repeat. Real numbers are all these numbers. Real numbers include all the positives, all the negatives, fractions, decimals, everything. That's what we work with most of the time, are real numbers. Now, some of what I just talked about is explained below. I will point out here, right there, the real numbers are kind of a different beast. You can't make a list of them because between any two real numbers, there's an infinite number of numbers. Think about that. They're infinitely dense. I can pick any number like 1 and 2, and there's an infinite number between them, like 1.1, 1.11, 1.111, 1.1111. I can keep going forever. And I can pick any two, like 1 and 1.1. There's an infinite number of numbers between those two. They're infinitely dense. And again, you can't make a list of them. Neither can you of the rational numbers, the fractions, the irrational numbers, or the real numbers. Now, they have some examples here, and I zoomed over this before. You can look at these when you get to the questions. These are your questions. Notice that the answers are in here. That's so you have more examples. I only assigned one question like this one right here, B, because it's tedious. You got to make a table. So on the question like this in the book, you'll make a table, and you'll classify them, and you'll put them in order from least to greatest. That's the A and the B. So there's only one question in the homework like this because I understand that they're a pain. So I skipped some of the others. But there's some more things you need to know here. Roster notation. Now these brackets here are actually called set brackets. Roster notation is just when I write a number out as a set brackets, and I'm just listing every number. They don't have to be in order. It's just a list of numbers. Now this set you see right here, 1 through 15, is a finite set. Finite is the opposite of infinite. It means there's a limited number. I can count them. Whereas infinite means unlimited. It goes on forever. I can't count. So the set right here in this set brackets, 1, 2, 3, 4 with the 3 dots, goes on forever. These are the natural numbers. That's an infinite set. Now, if we're talking about the real numbers, like right here, and these are the real numbers in this example, you've done this in algebra. Every number between 3 and 5 I'm talking about, including decimals, there's an infinite number of numbers between those two. Notice that there's no equal between the less than on both sides. X is greater than 3 and less than 5. There's no equal. That's why these circles are open. We're not including the 3 and the 5. If I put an equal below, then that means I'm going to include the 3 or include the 5. If I put an equal over there. Now, this idea is important because this leads us to a new notation you've never seen before called interval notation. When you look at 3, 5 below, it looks like an ordered pair. It does. But it's not an ordered pair. This is another type of notation for an interval. When you use a parenthesis, that means you're not including the 3. This is all the numbers between 3 and 5, and I'm not going to include the 5 because I'm using a parenthesis, or include the 3. So these two are exactly the same thing. So when I look right here, these two are the same thing. No difference. If I use a bracket, and they mention that right here, when I use a bracket, like if there had been a bracket instead of parentheses, that means I include the 3. So it'd be like putting an equal to in the above statement, x is greater than or equal to 3, and in the graph, the dot would be filled in. So there'll be examples here in a second, so if you're getting lost, just hang in there. The bracket means I include the 3, or if I put a bracket over here, I include the 5. So if I put brackets on both sides, it'd be an interval between 3 and 5, and it would include 3 and 5. So in this graph up here, the dots would be filled in. Sometimes an interval can go to infinity, like x is less than 2. It could go to, in that case, negative infinity or positive infinity. So you can do intervals. Instead of a 3, you can put it in a negative infinity, or maybe instead of a 5, you can put it in an infinity. And they have examples of that right here. So in this case, x is less than 3. Notice the open circle. There's no equal. It goes forever in the negative direction, so that's why it's negative infinity. We can't include negative infinity, no bracket. And it's less than 3, so it couldn't be equal to 3. If there was a bracket here, then it could be equal to 3. That's like this one below. Notice that solid filled in dot, because x is greater than or equal to negative 2. And I'm going to include the negative 2. Notice the bracket instead of a parenthesis. But I'm going to go forever in the positive direction to infinity. And again, I can't include infinity. Infinity is forever. So no bracket over there. Here are the numbers between 2 and 4. Open circles. There's no equal. And again, I'm not using brackets. I'm using parentheses. I'm not including the 2 or the 4. Here are the numbers between 1 and 3. I'm including the 1 and the 3. That's why they're equals. And that's why I'm using brackets on my interval. So that isn't too bad. Probably a more confusing one here is the set builder notation. It's not a big deal, but it takes some getting used to. This means the set, remember these are set brackets, the set of all numbers, x, basically the numbers that satisfy this condition. The little bar means such that x is greater than 8 and less than or equal to 15. So it's between 8 and 15. It could be equal to 15, but not 8. And x is a natural number. Remember, there's no decimals, so this would be a bunch of dots. So the set of all x such that x is greater than 8, less than or equal to 15, and x is a natural number. This little funky e here means an element of. X is an element of the natural numbers. It means it's contained within the natural numbers. I know that my x is, so there's no decimals. This would be a bunch of dots. I guess you could put an open circle on 8 if you wanted, but you'd fill in the circle on 15, but we're not doing any shading, it's just dots. I probably wouldn't graph the 8 at all. I'd start at 7 and put a solid dot. So they have some examples here, set builder notation. Sometimes there's a few homework questions like this, so this is a good thing to refer back to. Notice that sometimes you can't do roster because if you're talking about real numbers, an interval, you can't list them all. It's not possible to list all the real numbers. Notice they use the word or in here. So x is less than 1 or x is greater than 1. Oh, there's another way to do that. All numbers but 1. The set of all x such that x can't be 1. Notice how they didn't say, like here, it's an element of something. If they don't put that, that means they're just talking about the real numbers. So if they don't put an element of, assume it's the real numbers. So you're going to see some examples here. Refer back to this when you get to the homework. Here we have the set of all x. This is this last example, set builder, such that x is greater than or equal to -1 and x is less than or equal to 5. This takes getting used to. Don't panic. You'll see it a lot. You'll get used to it. All right, here you have your homework. And just point out a couple things. I only signed one, number 4 here, where you have to make a table and put them in order least to greatest. That is like this question right up here. So that's a little tedious, but I only assigned one of them. You're going to get confused on number 8, but hint, what's n minus n? Anything minus itself, it's 0. 1/2 times 0 is 0. So that means x would always be 1. In words, 1, O-N-E. Take a look at some of the examples to fill this out. There's some leeway here. Like on 10, you could say, how about whole number multiples of 5? That would work. You probably come up with all kinds of ways to do this in words. So think about this. Roster notation means you're going to list them all. Integers, remember there's no decimals or fractions. And then all we're doing is 26 through 34. I will point out again, this table that you see there is very much like this table you see right here above example 3, so that should help you. Notice that again some of them can't be done, and yes, that means when you get to those questions some of these can't be done. A couple of these are weird, like 26. Set builder notation, the book gets away with saying and x is even. X is negative integer, or how about less than or equal to 2, and x is an integer, and it's even. There's lots of ways you could do this, and we can talk about that when we meet together and we get to the assignment. If you have a question, I can help you with all of these, because if you have questions, but you need to try them. Always try everything. Yeah, okay, so important ideas, and I'm done. Just take a few seconds here. So you need to be aware of what elements are. You need to know what the types of numbers are, and yes, you'll use some of these in a variety of situations. Make sure you understand all the different types of numbers and how to list them. Make sure you know what roster notation is, when you just list a set of numbers, what finite and infinite are. An interval notation, where it looks like an ordered pair. A parenthesis means you don't include, a bracket means you include. And set builder notation, we use this a fair amount, so you will get used to it. And that would be it.